Today we're going to take a look at an enrichment on nonlinear inequalities. This actually is getting into something you would do in Algebra 2. So quick review. When we solve a single variable linear inequality, such as this one, remember the first thing we do is we change it to an equation. And then we solve it like an equation. So we move our x around, get it down to the end. Then we make our number line. So we'll do a quick check here on 0. It tests out as false, so I know whatever I'm doing, I'm shading not 0. So there's my open circle on -2/5 and shaded not towards 0. And then I do need to write that final inequality, x is less than -2/5. That's single variable. Now, there are people who've asked me, isn't there a different way of doing this? Aren't there like shortcuts? And there is a more traditional way to solve a single variable linear inequality. Let's look at this same inequality again. What I'm going to do is keep it as an inequality, and I'm going to start solving. So same steps I did before, only when I get to the end, there's a rule. Anytime you multiply or divide both sides of an inequality by a negative number, you have to flip the symbol. And that's how you get the less than -2/5, even though you started with greater than. And it comes from the fact that if we look at inequalities, 4 might be greater than 2, but as soon as I make both of those negative, like multiply by a -1, the comparison becomes -4 is less than -2. Negatives tend to flip around all the comparisons. Something we learned when we first learned about negatives, that even though 10 might be greater than 1, -10 was smaller than -1. It's that nature of the number line. So you could solve in a traditional sense, keeping the symbol, so long as you remember this little rule at the end. You have to remember if you multiply or divide both sides by the negative, you've got to flip your symbol. So then what's the difference between this and nonlinear? Well, a nonlinear means any equation we've ever solved could just be an inequality. And since we've been doing quadratic equations recently, let's focus on quadratic equations. We're going to do these the exact same way we do the linear kind. But now here's the thing. That number line testing strategy, it isn't just sort of a backup. It's actually required. And that's why solving linears the same way is such a good idea. You're developing a skill that you can apply then to every inequality you ever have to solve. So in this particular instance, we're going to do something we call interval testing. So let's take a look at a quadratic problem. Here you go. Pretty basic. X squared plus 5x minus 24 is less than or equal to 0. Just like before, I'm going to change that to an equation. Well, that's good old quadratic equation. I think I'm going to solve that one. I think I'll factor. So I get x plus 8 times x minus 3 equals 0. So x is -8 and x is 3. Now, I'm going to go to the number line. I'm going to put the circles on. I started with less than or equal to, so I am going to use the filled in circles. So here's the beginning of my number line. What you notice, though, is now you have 2 points. These 2 points are going to create 3 different intervals. So the first interval is from -8 down. The second interval is between the -8 and the 3. And the third interval is the above 3 side. So you have 3 different areas. You got to figure out where are the solutions living. To do that, you want to test a number that comes from all 3 areas. So I tested -9 from interval 1, and that was false. I tested 0 from interval 2, and that was true. And then I tested 4 from interval 3, and that was false. That means that my answers are interval 2. So I'm going to go shade that. There we go. Now that it's shaded, I'm going to write the inequality that I graphed. And that is that -8 is less than or equal to x, which is less than or equal to 3. Or x is between -8 and 3 inclusive, or you could say x greater than or equal to -8 and x less than or equal to 3. So you can see this came out a little different, and it's pretty intense. So why don't you try one? Here's a problem to try. You can pause it, and then when you're done, come back together and we'll see how you did. All right, the solution. So I changed to an equals, and I factor out the negative, GCF, and then I factored the remaining quadratic, and I get down to x is -3/2 and x is +1/3. So then I put my two circles on -3/2 and +1/3, and I looked at my three intervals. I tested -2 from the first interval, and it was true. I tested 0 from the second interval, and it was false. And I tested 1 from the third interval, and it was true. That meant that my shadings occurred in both intervals 1 and 3, the opposite sides of the circles. So then when I wrote the inequality at the end, I was graphing x was less than -3/2 or x was greater than 1/3. I have two different regions, so I use the word or to show that I'm doing this side or that side, the left shading or the right shading, because I can't be both at the same time. I can't be in the right shading and in the left shading at the same time. Now, you might still be thinking, well, what's the deal here? Like, why couldn't we have just solved it like we do with linears? Just keep the symbol and go. Well, here's what it would have looked like. I would have factored. We'll go back to that first easier one. I would have factored. I would have gotten the two answers, and I would have gotten x less than or equal to -8, x less than or equal to 3, but that's not what the answer was. It was x greater than or equal to -8 and x less than or equal to 3. So you might say, oh, that's fine. All we'll do is just if we get a negative answer, it just means flip the symbol. Well, I wish I could tell you that were true, but it's not. So let's look at this one. X squared plus 12x plus 20 is greater than 0. So I'm going to do it the way I need to. Set it equal to 0 as an equation, factored, x plus 10, x plus 2, solved. I got two negative answers. I put my two circles, open for greater than, on -10 and -2. I tested -1 in the first interval. It was true. I tested -5 in the second interval, which was false. And I tested 0 in the third interval, which was true. So I ended up with one of those opposite ways kinds of graphs. X was less than -10, x was greater than -2. Had I tried to just solve it, I would have gotten either they both were greater than, or if I said, oh, the negative ones get flipped, then they both are less than. And you might say, well, what about if we always flip the smaller one? You start to get into these kind of games, and you always will second guess yourself. The only way to truly make sure you are knowing what you're doing is by interval testing. That's why this is such an important skill to master, even in the linear world, because then it becomes a habit. So here are two more. Why don't you see if you can tackle these, and then come back and see how you did? So welcome back. Let's look at all the solutions. So on the first one, I had to GCF out an x when I changed it to an equals. Then I had to factor the quadratic that was left behind. And so then when I solved, I actually had three solutions: 0, 1/4, and -5. Now, with the number line program I was using, it was really hard to put the circles. It didn't let me adjust my number line. So when I went to do my shading, I did change the shading to purple so that you could see what was going on. With 3 dots on the graph, that created 4 intervals. So I tested -6 from the far left interval. It was false. I tested -1 from the -5 to 0 interval, and it was true. In the 0 to 1/4 interval, that little teeny spot between the two dots that you really can't see, I tested 1/8. And that was definitely false. And then I tested 1 from the far right interval, and it was true. So what I ended up with is that interval 2 between -5 and 0 was true, and interval 4 greater than or equal to 1/4 was 0. So that's where my two sets of solutions come from. It's between -5 and 0 or greater than or equal to 1/4. So you can see, again, interval testing was really important here to know which way everything goes. Because we got 0 as one of our answers. Had we kept the original symbol, it would have said x greater than or equal to 0. Turns out it was x less than or equal to 0. So it's always this game of interval testing. Let's go over to the absolute value problem. Change it to equals. Now, of course, we know with absolute value, that means there are two conditions. So we had that 4x plus 2 is -10 or 4x plus 2 is +10. And so then solving on both of those got me -3 and 2. So I put my two open circles. I tested -4 from interval 1 and it was false. I tested 0 from the middle interval 2 and it was true. And I tested 3 from interval 3 on the right and it was also false. So my solutions were between -3 and 2, but not including those. And so my final inequality was -3 less than x less than 2. So at this point, if you want any feedback, you can send me a picture. I'll be happy to look it over. Hope you enjoyed this. I'm not going to give you anything more to do unless you want to try something. But just as an aside, by the way, those absolute value ones may show up later. Have a good day.